Once you've got your CV data imported successfully, and you've done that for all the scan rates, and you have modified the data in such a way that you are producing a plot of either US or IUPAC convention, then you can go on to evaluating the reversibility and the mechanism of the electron transfer event. So I'm showing you a plot from the previous video that I made for the reduction and oxidation of a redox couple represented in the US convention. And so remember, if I'm representing this in the US or Texas convention, then positive currents are reducing, also known as cathodic, which means that the peak current in the cathodic direction for this couple, remember this would be, if I have multiple waves, then I would write an IPC for each one of those waves. But for a single wave, then we define the IPC as the peak current in the cathodic direction right here. So that's the maximum, that's the inflection point here. And similarly on the other side, in the oxidation side, and negative currents, similar to this, we would call that IPA for the anodic peak current. And the voltage, or the potential at which those peak currents occur, get corresponding names. E, which is the typical symbol for potential, peak for the anodic current, and E peak for the cathodic current. So I have lines sort of roughly drawn where those intersect the x-axis, which is our potential curve. So what you do to evaluate reversibility and mechanism is to fill out this plot. And so you'll have access to this template that you can modify. And so you will be inputting the EPC, so that would be the voltage at which the current is a maximum in the cathodic direction, which would be the positive current if you're using US convention here. So you would go down here, find where this is the inflection points at a maximum. You can do that just by looking directly on this and clicking on the value here to find out what it is. Or you can look at the original data set and find where it goes to a maximum or a minimum. Either one of those would work sufficiently. Then you'll plug them in here. So here, V, or nu, is our scan rate. And so you're collecting these data over multiple scan rates. Here I have 4 scan rates, 100, 75, 60, and 40 millivolts per second. And then I have automatically, it's going to convert this column to the log transform of this value, which will be useful. And then this is the root transform of the original value, which will be useful. So you'll plug in these values because this is what you experimentally controlled. And then you'll extract the peak cathodic potential and the peak anodic potential. So both of these for each one of these scan rates, and plug those values in directly here. And then this column will automatically compute, which is really just the absolute value of the difference between these. That's what the delta peak is. So it's really just the difference in voltage between these two peaks of the wave. And then I multiply it by 1,000, so it's in units millivolts. It's just easier to read. Similarly, you'll grab the peak cathodic current, which will be read off the y-axis, and the peak anodic current, which will also be read off this axis. In this case, here's the anodic in the negative direction, and the cathodic in the positive direction. And then the last thing, so you'll plug those values in, and the last thing is to compute the ratio of those two terms, and the absolute value is all we need, so that will automatically be computed. At the same time, all 4 of these plots will be generated below. So the first plot is what the voltage difference is between the two peaks as a function of the log of the scan rate, and then below it is the same thing as a function of just the linear version of the scan rate. So generally speaking, a electrochemical reaction would be considered very fast and what we would call reversible, meaning it's so fast that the electron transfer at the electrode surface is controlled purely by diffusion and nothing else. Then what that means is if we keep changing the scan rate faster and faster and faster and sweeping the voltage, it doesn't matter because it's purely diffusion controlled. And so we would expect there to be no actual change in delta E as a function of either of these scan rates or the log transform. In this case, you can see that it does change, and we can see that up here as well, right? As we change the scan rate from 40 to 100, we can see that the delta P goes from 161 millivolt separation to 200. And so that's indicative of a system that's either quasi or irreversible. The larger the delta P, the more irreversible it is. And so that's the sort of first evaluation of reversibility. The other aspect of reversibility has to do with the symmetry of this plot. So in this case, the current in the cathodic direction up here is very, very similar and symmetric to the current in the anodic direction, which means whatever gets reduced, almost equal amounts of it then gets reoxidized as we turn around and start sweeping the other direction. That's indicative of, again, something that's pretty fast and quite reversible or quasi-reversible, depending on what the exact delta E is here. If you start to see one of these humps decrease relative to the other one, then that's indicative of the fact that you're moving towards an irreversible system. In the extreme limit, you would have just one bump, and then upon reverse, it would be completely flat, which would mean that the second that you reduced that species, it immediately went and got transformed into something else, which made it not possible to be oxidized in reverse. That would be a fully irreversible process. So the other two plots here that automatically get generated are useful for evaluating the mechanism. And so we're not going to go into great detail in this video, but it'll be described in class and in your labs. But similar to the discussion we just had, if we took the ratio of the peak anodic and the peak cathodic currents, which is really just that point and this point divided by each other, and remember, you're going to be measuring this relative to, ideally, where the line flattens out, not from zero proper. So even if you didn't do that, it wouldn't matter. The plot would still give you the same shape, but it wouldn't reach 1 likely. Often this curve is shifted up or down relative to 0, so taking the absolute values of the current at the maximum isn't going to be the best representation. Instead, if I wanted to measure IPC, the cathodic side, I would measure it relative to sort of this flat line here, because that's essentially when the current goes to 0 for this process. And for the anodic peak current, our IPA, I would measure it relative to this flat line here. So you can see that those aren't the same as 0, so they won't give me the same number, but the trend is true. So if I look then at the trend where I make a plot of the ratio versus scan rate, in principle, if this is a nice reversible process that is, or even quasi-reversible process, where the process is purely electrochemical, meaning that there's no subsequent chemical reaction that's stealing one of the species once it gets oxidized or reduced, then we'd expect these two peaks to be the same size, which is what a ratio of 1 tells us. But if this starts to deviate away from 1, what we would typically see is that at really slow scan rates, so that the limit of slowness down here, we would expect this to be for a system that has a subsequent chemical reaction. We would expect that subsequent chemical reaction to be stealing some of that particular species away and make it not possible to oxidize or reduce. And so the slower we scan, the more likely we'll have a ratio that's not 1, because we're allowing that chemical reaction to grab that species. But if we keep ramping up the speed at which we're scanning this, at some point, the speed at which we transfer those electrons is faster than the subsequent chemical reaction, which means that we would converge at 1 eventually. And so if you get shapes of this plot, where it's sort of concave, it's starting down here closer to 0 and converging at 1, or the other direction, starting high and moving towards this direction, that's indicative of what we call an EC type reaction, or electrochemical chemical, meaning you transfer an electron from the electrode and then a subsequent chemical reaction changes that species. If over the entire scan rate range you don't have any change, should be close to 1, but it doesn't change nominally like it does here, then we would call this just a purely electrochemical mechanism. And so those are the data that we would use to evaluate reversibility here, where it's unchanging, delta P is unchanging with either the log term or the scan rate in the linear form. And then mechanism, we look at this plot